Hello everyone, my name is Paulius Velesko. I'm an application engineer at Intel, and I'll be going a little bit over KNL architecture. Supercomputers achieve high performance by using layer upon layer of parallelism. So we have parallelism on a system level between nodes, which we normally exploit through MPI. We can have parallelism within a node in the case that a node has multiple sockets. But then within a socket, we have parallelism by having many cores. Within a core, we have instruction level parallelism because KNL is a pipeline processor, so it can be executing multiple instructions simultaneously. And then we have parallelism within each instruction. So these would be SIMD or vector instructions, where each instruction will be operating on different elements. And then finally, within each operation, we can also have parallelism in the case of, for example, FMA, where we have a multiply and an add operation being performed on each operation. So KNL is a second iteration of Xeon Phi processor line, which has some notable improvements over the first generation, which was called KNC. So first of all, it's a self-booting system. It's pretty much a regular processor, unlike KNC, which was a PCI Express accelerator. So it's binary compatible with Xeon, meaning that you compile your application for older systems that are Xeon based, you can run them on KNL. The core itself is an Atom based processor compared to the previous generation, which was a Pentium based architecture. It has improved vector density that comes with a new instruction set, which is AVX 512. It has a scatter gather engine, which helps with indirect memory accesses, both loads and stores. It has a two-tier memory layout in the sense that we have MCD RAM and DDR memory that's accessible on the node itself. We have a built-in OmniPath NIC controller, and the core is connected through a 2D mesh topology, which again compared to KNC, which had a ring topology. This is an architecture diagram for a KNL. So you'll see that the KNL chip is split into 36 tiles. Each tile consists of 2 cores and an L2 cache slice. All the slices are connected together. They're cache coherent and make up essentially what you see as a last level cache. So for the highest end KNL that has 36 tiles and 72 physical cores, we'll have 36 megabytes of L2 cache. So we have 16 gigabytes of fast MCD RAM memory available on the KNL, and these 16 gigs are made up of 8 stacks. These 8 stacks of memory are accessed through the EDC, which stands for Embedded DRAM Controller, and they're scattered throughout the chip. And we have a total aggregate bandwidth of 485 gigabytes a second. In addition to that, we also have 6 DDR4 memory channels that are being serviced through 2 controllers that you'll see here on the side, and we support up to 384 gigabytes of external DDR and a maximum bandwidth of about 90 gigabytes a second. And finally, node-to-node communication is assisted by having an integrated NIC on the package. That's OmniPath, and it's connected by PCI Express. So all of the cores within Knights Landing CPU are connected using this 2D mesh. So this 2D mesh is responsible for moving data between all the different tiles and components on the chip. So it has YX routing, meaning messages will first go in the Y direction and then move in the X direction. The chip itself, since the L2, or more like last level cache, is composed of all of the L2 slices within the chip, the chip itself is cache coherent and uses massive protocol for invalidating and evicting cache lines. And this is configurable, so you can configure KNL to have different clustering modes, all-to-all, quadrant, that I'll talk about in a second. Let's look at an example. Tile 1 requests for memory at a certain address, and we look at our L1 cache and it's not there. We look at our local L2 cache that's within our tile, and we find that the data is also not there. So then we need to figure out where exactly does this data live. The addresses are hashed into a distributed tag directory, and each tile has a slice of this total distributed tag directory. So we go from tile A to tile B, and tile B contains the tag that's associated with the memory address that we're interested in. So tile B then tells us that, hey, this cache line that you're interested in is cached, but I don't have it. It's actually in tile C, so go there. And then we go to tile C, we look into the L2 cache, we find the data that we're interested in, and finally we forward the data back to tile A that originally requested it. So since we're on the topic of cache operations, here's a good tip, and that is use streaming stores. So whenever you write something to a location in memory, normally the compiler will first do a memory load and load that cache line into your cache, then change the data, and it might skip writing back to memory. But if you have a case that you're writing to memory and you know that the data that you're writing is not going to be used anytime soon, you can tell the compiler to use these streaming stores, also called non-temporal stores, to bypass that first step of loading into your local cache, and that can actually increase your bandwidth. So if you look at this table here, you'll see that, for example, using 120 threads with MCD RAM being flat, we go from 350 to 463 gigabytes a second of bandwidth if we use streaming stores compared to not using them. In the previous example, I showed you what happens when we have a miss on the local L2 cache, local to the tile. So whenever that happens, we ultimately have to look in the tag directory, distributed tag directory, to figure out how to further service that request. So the way that memory addresses are mapped onto the distributed tag directory is configurable, and this configuration is what we call the cluster modes. So essentially, cluster modes change the path that your request will take from the tile that missed it to the memory controller, and finally back to the tile. So we have the most basic one, which is all-to-all, in which there's no relation between memory address and the tag directory where it's going to live. We have hemisphere and quadrant, and these essentially guarantee that the tag directory and the memory controller are going to be within the same hemisphere or quadrant. And finally we have SNC, which stands for subNUMA clustering modes. So these further reduce the latency, but at the cost of creating additional NUMA domains that we'll need to take advantage of through software. So in case of all-to-all, we have a memory request coming in from tile 1, and we see that this memory is not cached in our local L1 or L2. So we look at the tag and search through our tag directory and see that this tag is not in our tag directory. So we need to go and to tile 2, and we find our particular tag is in the tag directory of tile 2, but the memory serviced by this particular tag is actually serviced by the EDC all the way at the top. So then we have to go to the EDC. We fetch the memory from, in this case, CD-RAM, and once that is done, only then we can go back and forward that memory back to tile 1 that made the request. Now, in case of the quadrant cluster mode, the primary difference is that the addresses are mapped to tag directories in such a way that the tag directory will be in the same quadrant as the EDC that's supposed to serve that particular tag. So again, we have a similar situation. We make a request from tile 1. It's not an L1 or L2. We then go to the tile that contains the tag that we're interested in, and we find the tag. Now this tag is, now the EDC that will serve this tag is much closer to us than it was in the all-to-all mode. So we go to the EDC, service the request, and give it back to tile 1. So as you can see in this example, we've reduced the number of hops from 22 to 14. So there's one more improvement that can be had here, and that would be if the tag directory was also close to the tile that originally made the request. But the issue is that the number of entries in the distributed tag directory is limited. So in order to achieve that level of affinity, what we can do is we can split the address space into 4 or 2. So that would be SNC2 and SNC4. So we can split the address space, and now each quadrant will service a particular address space, and it will allow us to further reduce the number of hops required to service L2 miss. So if we do that, we go from 14 hops to 10 hops in the case of SNC4. So this gives us the best performance, but now we have, instead of 1, we have 4 total NUMA domains, and with additional NUMA domains there's some affinity considerations. So we have to change the way that we run our application in order to ensure best performance using SNC4. In addition to being able to configure the clustering mode, the MCD RAM configuration on the KNL is also configurable. So there's 3 primary types of configuration that we have. We have flat, cache, and hybrid. To this day, I'm yet to see a practical example of someone using hybrid mode, so I will not talk about hybrid, but I want to mention flat mode and cache mode. So I've talked about multiple KNL clustering modes, and you might wonder, well, which one is right for me? So while there's 5 or 6 total, in practice we normally default to using quadrants. There are cases where you might benefit from using SNC4. So in particular, if you have an application that already has OpenMP and MPI, you're in a very good position to try out SNC4 with minimal effort. In particular, if you have an application that you normally run with 4 MPI ranks per node, that would be the perfect case for trying out SNC4. And remember that SNC4 primarily deals with cache latencies. So if you have a code that's latency sensitive, you might want to invest some time into exploring SNC4. And if that's not the case for you, then you can stick to quadrant mode. The default configuration on Theta is for the nodes to boot into cache mode, where the 16 gigabytes essentially act as your last level cache. So essentially you get a boost in memory bandwidth without having to do any work. But you can also configure your KNL nodes to run in flat mode. And what that means is that your 16 gigabytes of MCD RAM you'll get a separate memory space that you can then use, and using that you will be able to achieve the maximum throughput available. So if you look at these triad examples, you'll see that the best bandwidth that we were able to achieve with cache mode is 352 gigabytes a second, whereas if you switch to flat mode, we're able to get 485. So if your application uses less than 16 gigabytes of memory per node, you can just switch over to flat mode and then use NUMA control to pin all your memory allocations onto the MCD RAM and then get high bandwidth memory without having to do any changes to the code. If your application uses more than 16 gigabytes, you can also tell NUMA control to prefer allocations on the MCD RAM and then spill over to DDR if you run out of memory on MCD RAM. Or you can manage your allocations by hand using memkind library. So whenever you request some compute nodes from Theta, the default mode is for KNL nodes to be booted into quad cache mode. So if you want your nodes to be booted into a different mode, you can follow this link at the top, and that will tell you which attributes you need to specify whenever you submit your JavaScript in order to change which exact configuration you want the nodes to be given to you in. And when you do that, then we have this tool, NumaCTL, and we can pin these MPI processes to one of the NUMA domains. For example, one of the 4 NUMA domains that we get with SNC4. So at the example below shows you exactly how to run your 16 rank node with different ranks being attached to different NUMA domains for example, per memory. We have 2 CPU cores sharing, living on the same tile. So within each core, we have 2 vector processing units. The tile itself has a 1 megabyte slice of L2 cache. So this cache is 16-way associative. We have 1 cycle for read and 2 cycles for write. In addition to that, we also have this CHA, which is a caching and homing agent on the tile itself. So the tag directory is going to be in this caching agent, and in general, this caching agent just implements cache coherency between the entire mesh, and it is our primary connection to the interface to the mesh itself. So the KNL core itself is based on the Atom Silvermont microarchitecture. It is a pipeline out-of-order processor. We have 2 decode, rename, retire units, and we have 2 vector processing units for AVX512. So that essentially means if we don't have any bubbles in the pipeline, every cycle we can execute 2 AVX512 instructions. If you look at profiling results from something like vTune, for example, if you do microarchitecture analysis on the KNL, you'll see that in the vTune, our applications are kind of split. There's a percentage front-end bound, percentage back-end bound, and percentage retiring. So if we don't have any bubbles in our pipeline at all, everything is kind of running in a perfect case scenario, then we're not going to be front-end bound, we're not going to be back-end bound, we're going to have 100% retiring. But if, for example, we're struggling with fetch and decode, maybe we're missing instruction cache and we have some latencies there, we're going to be a little bit more front-end bound. But most of the time, we're going to be back-end bound, and that just means that there's bubbles in the back-end pipeline. and those can be, instruction dependencies, or maybe even just latencies from accessing different portions of memory. If we have an instruction that needs a piece of data from memory, or it needs a piece of data from an instruction that came before it, scenarios like that introduce dependencies and latencies in the pipeline, or we call them bubbles. So whenever there's a bubble in the pipeline, nothing can be executed on that particular stage of the pipeline in this instruction stream. So what KNL does is actually it supports 4 hardware threads per core. So we can run 4 OpenMP threads per core without additional overheads. And what happens is if you're executing instructions from thread 1, and we have some sort of a dependency, say we have to get something from memory, maybe we have a latency. So this latency can be hidden. So we do that by switching out thread 1 for thread 2, for example. So the instruction stream coming from thread 2 will fill in the empty slots in the pipeline, and then so on for threads 3. And threading works by filling in bubbles in the pipeline with useful work from instruction streams coming from the additional threads that we have support for. Using hyperthreading generally helps with hiding latencies. So those can be costly math operations, for example, if you have to do a square root, or hiding memory latencies. So if we have to wait for some data before it comes from memory, we can swap out a thread and do instructions within that thread stream that don't have any dependencies. And one other important piece to remember is that by introducing hyperthreading, we don't replicate all of the compute units inside the thread itself. So there is a requirement to have a certain instruction mix. So for example, we have vector processing units and integer processing units. So if you have an application that does a little bit of integer, a little bit of floating point, that kind of application would be a prime target to take advantage of hyperthreading. If you're interested in exploring how hyperthreading affects the performance of your application, or maybe a particular kernel that you have, we can do some testing using OpenMP. So in this example, I do export OMP num threads equals 4. So I will create 4 hyperthreads, and then we need to use OMP places to pin those threads to a single physical core. So the way that the cores on the KNL are numbered, we have cores 0 through 64 are being physical cores. And then, so for example, for a 64 processor, right? So the hyperthreading slot number 2 on that same physical core would be offset by 64, and so on until we get to the total maximum number of threads we have. So the OMP places example that I have here, we have 165, 129, and 193. So these are all tied to the same physical core, not the first core in the mesh, but the second core. And I normally set that. I normally use the second core just because I want the operating system to be running on core number 0. So I don't want to be conflicting with that. So it gives me a more accurate test. And then this is an alternative method. You can set your placement for OpenMP threads to threads as opposed to cores or sockets, and doing OMP prog bind equal to close will make the OpenMP runtime to place all of those cores one after another, packed tightly together, as opposed to spreading them out around the core. So one issue with this alternative method is that It doesn't let you do explicit pinning to a particular CPU core. But if you want to run a test with more than just 4 threads total, then you can use this alternative configuration. So I just wanted to illustrate the impact of hyperthreading for some example. So in this example, we have just essentially just the memory read. We're using complex doubles, and these doubles are accessed through an indirection matrix. So on the left here, you have a total memory footprint of 1 megabyte, and we know that 1 megabyte is the size of cache for a single tile. So we know that we should be getting very, very good performance. We should not be going out to main memory. And if we're not going out to main memory, we're not going to have a whole lot of bubbles in the pipeline. And if there's no bubbles in the pipeline, then essentially we will not be taking advantage of those additional instruction streams that are coming from using hyperthreads. And that's exactly what the data shows. So we'll see that going from 1 to 2 all the way to 4 hyperthreads does not increase our performance. We get the best performance with using just a single thread. So I didn't mention on this column here, we have a percentage of random access. So this metric tells you the likelihood of a cache hit given this indirection matrix. So we see that hyperthreads don't help in this very small case. But if we go to this other example, with a much larger memory footprint, we're now using 100 megabytes. We know for sure that we're going to be hitting memory very often. And as you can see in this example, we do achieve the best performance using four hyperthreads. And that is exactly because we have to wait for things to come from memory, and while we're waiting, we can substitute a different thread and have more instructions in flight. KNL uses AVX 512 instruction set, and unlike previous vector instruction sets, this one is not a monolith, so there's extensions to AVX 512. So all AVX 512 implementations have a foundation, and these essentially deal with having larger vector registers, but the instruction set itself can have extensions, for example, conflict detection or scatter gather and fast reciprocals. So whatever application you had on the previous generations prior to KNL, those applications can be run directly on a KNL because it's backwards compatible to all the previous x86 and vector instruction sets. But keep in mind that you are likely not going to see the best performance if you don't recompile your application to use the wider 512 registers. And in addition to that, you will not get optimal performance if you don't optimize your code to take advantage of these wider registers. This concludes my presentation. If you have any additional questions or comments, you can reach out to me via email, and you'll find my contact information in the introduction